Hello, this is Sumit Kumar Arse. Welcome to my YouTube channel. I am from DAVV IIPS and my roll number is IT2K2487 and my enrollment number is DE24022295. And today we are going to see our question number 3 of our internal one of NAD. Okay. This is our third video. In previous two videos we have solved our question number 1 and 2. Here we will see our question number 3. So let's see what our question number 3 is saying. So our question number 3 is saying how are polynomials represented in computers. Okay, write an algorithm or flowchart to evaluate the polynomial. Okay, p of x is equal to a n xn plus a n minus 1 x n minus 1 to the a1x plus a0. Okay, and we also have the sub part of our question, which is a part is compare the efforts number of multiplication and additions of a brute force method with the recurrence relation. Okay, and b part is write the recurrence relation of dividing this polynomial by x minus r. Okay, so let's start. So let's see how our polynomial are represented in computer. Okay, so see a polynomial p of x which is given here, that is a n x n plus a n minus 1 x n minus 1 to the a1 x plus a0. Okay, this is represented in a computer using an array or list of coefficients. Okay, so array representation is like this. Here in table you can see index I having 0 1 2 3 till n and coefficients of ai like a0 a1 a2 till an, and term represented a0 a1 into x a1 into x square a3 into x cube like an into xn. Okay, so alternative also we have descending order storage. This is like a0 is equal to an, a1 is equal to an minus 1, an is equal to a0, like in reverse order, descending order. Okay, so both are convenient to the user, and it depends on the user how what they have to choose. And okay, now see method 1, which is our brute force. Okay, this is also our direct evaluation. So see, in this method each term ai xi is computed independently. Okay, by calculating our xi. Okay, from scratch each time. Okay, nice. So algorithm we will see for this is first we will start, then we will read our coefficient a0 a1 till an and the value of x. Then next we will set our result to the 0. Next in step 4 we will make that for I is equal to 0 to n, and then and in that only we will compute our power to x to the power I, and then compute terms ai into power. Okay, and then we will make our result is equal to our result plus term that is one addition. Okay, now we will print our result, and this is our algorithm for this, and step 6 as we will stop it. Okay, so now we will see the effort count of this brute force for a polynomial of degree n with n plus 1 terms. We can see here our table terms x to the power I, that needs multiplications ai into x to the power I multiplications and addition to our result, addition to result. Okay, and then this is our table down here total, and you can see this. Okay, now we will see our next method, that is method second, and which is recurrence relation, and that also our honors method. Okay, in this honors method rewrite the polynomial using a nested recurrence form that avoids computing power of x separately. This is the most efficient method. Okay, now see, Honest nested formula is this: p of x is equal to a n xn plus a n minus 1 xn minus 1 to that, and that is equal to our to the a n x plus a n minus 1, and this whole into x plus a n minus 2, and this into x plus and that is so up to into x plus a0. Okay, now our recurrence relation is defined: bn is equal to an, bk is equal to ak plus bk plus 1 into x, and for k is equal to n minus 1 n minus 2 till the 1 and 0. Okay, now then p of x is equal to b0. We will see algorithm for our this method, and that is like this. First we will start, and then in step 2 we will our read the coefficient a and a n minus 1 till our a0 and the value of our x. Okay, now in step 3 we will set our b is equal to an and initialize with leading coefficient, and in step 4 we will make our for k is equal to n minus 1 down to our 0, and then b is equal to b into x plus a k, which is our 1 multiplicable plus 1 addition per step, and in step 5 we will print our b. This is our p of x, and that's it. Step 6 we will stop. Okay, now effort count we will see for Horner's method. In this, each iteration of the loop perform exactly one multiplication and one addition, and the loop runs n times and for from k to n minus 1 down to 0. Okay, iteration k, here we will see iteration k operations, multiplication, additions, and you can see in this table from k is equal to n minus 1, k is equal to n minus 2 to k is equal to till 0. Okay, so here at last we will also total. Okay, now we will see our part 1. Part 1 comparison Booter force with recurrence relation, and this is our method. In this down table, here is our method: multiplication, additions, and total occurrence, which is you can see Booter force, Horner's recurrence, and saving BF Horner. Okay, in this you can see n plus 3 by 2 and n plus 1 by 2, and our addition is n 0, and our total operations is n plus 5 by 2 2n, and here n plus 1 by 2. Okay, now you can see here our when we have our numerical example n is equal to 4 with degree 4 polynomial, and you can see our n brutal force multiplication, Horner's multiplication, and multiplication saved. Here you can see how this is different from each, and this is how is this. Okay, now we will move towards our part B, which is recurrence relation for division by x minus r. So when we divide a polynomial p of x by x minus r, we get p of x is equal to x minus r into q of x plus r. So where our q of x is the quotation polynomial of degree n minus 1 and r is the remainder. Okay, now this process is known as synthetic division or Horner's synthetic division. Okay, so the derivation you can see of our recurrence relation is like that. We will take p of x is equal to a n x n plus a n minus 1 and x n minus 1 plus this to the a1 x plus a0, and qx is equal to b n to x n minus 1 plus b n minus 1 x n minus 2 to the b n b2 x plus b1. Okay, then p of x will is equal to x minus r into qx plus r. So this is our expanding of that. Now we will see our recurrence relation, which is bn is equal to an, initializing with leading coefficient, and bk is equal to ak plus r into bk plus 1, and here k is equal to our n minus 1 n minus 2 till our 1, and r is equal to b0, that is equal to a0 plus r into b1, the remainder. Okay, now the coefficients bn minus 1 till b1 are the coefficients of the quotient polynomial qx, and b0 is equal to r in the remainder. Okay, now here you can see our key property is by the remainder theorem, r is equal to p of r. So if r is equal to 0, then r is a root of our p of x. Okay, that's it. Now we will see our algorithm for synthetic division by x minus r. So in this we will, first step is to start, and second we will read our coefficient an minus 1 to our a0 and the value of r, which is our divisor root. Okay, next step we will set our bn to our is equal to an. Now in step 4 we will see our for k is equal to n minus 1 down to our 0, and then bk is equal to ak plus r into bk plus 1, and step 5 we will quotient q of x has a coefficient bn comma bn minus 1 to our b1. Okay, and next our remainder r we will set is equal to b of 0, and in step 7 if r is equal to 0, then our r is a root of our p of x, print our quotient and remainder, and that's it, stop here. Now see our one example. Let p of x is equal to x cube minus 6x square plus 11x minus 6 divided by x minus 2. So here you can see k, ak, bk plus 1 and r into bk plus 1, and at last bk is equal to ak plus r into bk plus 1. Here are the how it is done, and at last you can see what the result is, and you can see how it works. Okay, thank you.